to the Thursday. Welcome to the Thursday morning session of the microquasar workshop. The first talk will be on highlights of the Insight-HXMT X-ray satellite by Qinghui Bu. Go ahead, please.
Thank you very much. Good morning, everybody. My name is Qinghui Bu. First of all, I would like to thank the organizer for the invitation. It's been a great honor to give a talk on the Insight-HXMT mission. So my talk will be on the Insight-HXMT, time in the extreme universe in the high energy field. Wait, my mouse doesn't work. Sorry. Oh, here. My talk includes 4 sections. The first, I will give a very brief overview to the Insight-HXMT mission, and then I will briefly introduce the spectral timing correlations in X-ray binaries, especially in black holes. And the most important part will be the science highlights in the view of time analysis from HXMT result. And in the end, I will give a very brief summary of my talk. So the first will be the overview to the Insight-HXMT telescope. It was shot from the Insight Hard X-ray modulation telescopes. It has 3 telescopes on board of the HXMT. So the first one is a high energy telescope, which has the energy range of 20 to 250 keV for pointing. It has geometrical area of 5,100 square centimeters. And the second one is a medium energy telescope. It has a 5 to 30 keV range for the pointing mode, and it has area of about 1,000 square centimeters. And the last one, the low energy telescope, it had 1 to 15 keV for pointing, and it had the lowest area of about 400 square centimeters. For time analysis, besides the geometry areas for the photon counts, we also care about the time and resolution. For HE, we have about 25 microseconds resolution, and for ME, we have 280 microseconds. For LE, we have a very small resolution, about 1 millisecond. The core science of the HXMT telescope is to observe X-ray binaries in broad energy band and study the dynamics and emission mechanism in the strong gravitational or magnetic fields. So for time analysis, we care more about the high energy emissions compared to the ROSXT and even nicer. So what advantages do we have in the high energy emissions, high energy ranges? Sorry. For the first one, the large area, we have about 5,000 square centimeters areas of the detection, and then we have a high time resolution of about 25 microseconds. And the most important part is we do not have a pile-up effect. So when you combine all these features together, you will find the Insight-HXMT might be so far the best telescope that you can use for time analysis above 30 keV. So it's here in this energy range. For the last 4 years, the HXMT observations for the bright X-ray binaries have been, to be honest, frankly speaking, for the last 4 years, it's been carnival festival for the X-ray sources. We have observed many bright new X-ray sources like MaxCG 8020, this one, and also the MaxCG 1535 minus 571, and also the most recent one, MaxCG 3048. And we're able to trace the whole outburst of the X-ray sources. And besides a lot of the new rebitings of the known X-ray sources like Swift J6058.2 and ESCO 1862 and GX 339-4. So for HXMT, we're able to perform the continuously high cadence observations of the bright X-ray sources. In the following part, I will give a brief introduction about the spectral states divisions and also the correlated timing correlations with the spectral states, especially in the black hole X-ray binaries, before I go any further into the science output. When you look at the lower left panel of this diagram, you will see the Q diagram from typical black hole binaries during the outburst. So when the source goes from the outburst, it goes from the low hard state to the intermediate state and then goes to the soft state. The spectral the energy spectral shapes changes with different states. For example, at the low Hart state, you will see the spectrum is dominated by the emission from the corona. You will see a parallel shift spectrum with a very flattened photon index in the energy spectrum. And when it goes into the intermediate state with emission from the accretion disk increases, and the emission from the flux from the disk emission increases, I will change the shape of the energy spectrum, and then the lower part will start to increase. The slope will increase, and when the source involved to the soft state, at this point, the inner disk iridium is believed to reach the ISCO. So, and the spectrum dominates by the disk emission. So then you will see very broad features here at the low energy range, and at this point, the power index become become higher. So the photon index become higher. And how that is related to the time analysis we observed at different states. So here give you the general picture of the timing properties, aka the QPUs that you can find at the different spectral state. At the Hart state, especially for the low Hart state, the power spectrum is dominated by the flat top noise and the QPU type C QPUs on both of these broad features. And when the source involved to the Hart intermediate state, the QPU frequencies of the type C QPU frequencies increases. And when the source involved to the soft state, here you can observe the appearance of type B QPUs, but this is not necessarily observed in all the black hole sources. And then when the source involved to the high soft state, at this point, you can observe some of the type A QPUs. It's dominated by the red noise and the broad feature of these QPUs at this 10 to 30 hertz. But it has to be noted that the type A QPUs is very rarely observed in the black hole sources from our ROSI-ST data, because most of the black hole sources cannot transition to the high soft state.
So, quick interruption. Sorry, we have a slight problem because we don't see all of your screen here.
Sorry.
I think it's too wide.
But I can't see the screen from my laptop. So what should I do? Sorry, I don't know how to do this. Maybe
so
I should
try stopping sharing and then resharing again.
Yeah.
Okay.
Perfect. Don't touch anything. This looks good.
Okay. Okay, this way. Okay. Okay. Should I continue?
Yes, please. Thank you so much. Sorry for the interruption.
That's okay. Thank you. So by far, it has been proposed. Many models have been proposed to explain the QPUs and the broadband noises observed in the power spectrum of the black hole sources. One of the most promising models among most popular models is the one involved the Hart in the flow-length theorem precessions. And it was under the framework of the GR relativities models. And the model was proposed to explain the kilohertz QPUs and the low-frequency QPUs in the Newton stars, but later was applied to the black hole, the QPUs observed in the black hole sources. For example, in GIO 1655. In these observations, three types of QPUs was observed in the same observation: the low frequency QPUs and the lower high frequency QPUs and upper frequency QPUs. They use three frequencies that was described in the GR relativities models to explain the QPUs or generations. For example, the low frequency QPUs was arise from the length series precession of the model, aka the nodal precession frequency, and the high frequency QPUs, the lower one, is caused by periastron precession frequency, and the upper one is always the orbital motion frequency. But there's still a lot of the questions rise behind these models. For example, it cannot completely explain the IMS evolution, spectral evolution, especially in the low energy range, and also the time lag studies it shows correlations with the frequencies and also the orbit inclinations. So in the following part, I will introduce how HXMT result help to improve all these unsolved questions. Okay. So the following section will be the science highlights from HXMT in the view timing analysis. The first source, MaxG 8020 plus 070. So this source is by far the most brightest X-ray sources have been observed by X-ray telescope. It has a luminosity about 4 craft. Look at the low upper left panel, you can see the light curve from 1 to about 200 keV from LE to HE. And we studied the type C QPUs in the very hard state of the low hard state. As you already know, that the source have very strange or weird typical particular properties in the low hard state. It has the actual turnover at the low hard state. So we studied the type C QPUs in this state. This is the power spectrum that extracted from 1 to 250 keV. It is the highest QPUs we have ever observed by X-ray telescope so far. You can see the frequency that the QPU frequency doesn't change with energy, so it was fixed. It was constant at about I would say 40 millihertz. When you look at the time lag spectrum of this source, you will see the phase lags involved with the energy. It shows the soft lags all in the higher energy range. When the energy below 10 keV or 20 keV, it keeps constant at 0 lags, and when the energy increases to about 200 keVs, and the soft lags can reach to about 1 millisecond. And it raises the question about the origin of the soft lags, because if the hard photons are caused by the condensations in the corona, then you should see the hard lags in the lag spectrum instead of the soft lags. And if you consider this kind of soft lag is introduced by the light travel time, so it will correspond to about the size of the 10 to 4 RG for 10 solar mass black holes. So it will be too big, too huge to be physical like in this source. So, and also the QPU frequency doesn't change with energies. If you look at this plot, you will see the frequency is about 38 hertz always. So that would be a great, these 3 points, it raise the great challenge for the existing hot flow lens theory models. So therefore we propose these jet precision models based on the we propose these small scale jet precision models. In this model, it's described the jet twisted and rotates around black hole, and it has the different phase angles at the different part of this jet. It processes as twisted and rotates like around this one's the black hole. So it gives the different projection angles at the XY plane. So the different angle difference, the phase angle different from the different part of the angle introduce the phase lag. So in this way, you can explain the soft lag we observed in this source. And also, if you and in this model, we assume that the RMS is dominated or modulated by the jet speed, and observed flux is modulated by the Doppler effect and solid angle effect. And in this way, we can reproduce the observed feature, the time lag and RMS spectrum we observed in the source. So, and we further applied this model to this also new black hole sources, MaxG 6031 minus 479. So it can well explain the QPU RMS correlations with energy from 10 to 100 keV. I have to stress that in this model, we only consider the energy above 10 keV, because below 10 keV, their disk emission variabilities, the RMS includes the disk disk variabilities. So it is now it's a little bit complex to remodulate this to simulate, and also it can also explain the inclination angles, the time lag with energy. The time lag with energy. So I didn't see this. I don't have the plot here. So sorry. So in the right panel, it shows the similar light curve from the different radiums of the jet, and it will give you the phase lags between the different energy. So it will reproduce the time lag energy relation that you observe in the source. It can give you either a soft lag or hard lag, depending on the angle. But despite this model can well explain the MS correlations and time lag correlation, it has the small problems in explaining the time lag dependence with orbital inclination. For example, from Jacob's data work from 2016, they show that the black hole source have the time phase lag of black hole sources have very strong dependence with the inclination angle. For low inclination angle system, they have a little bit higher phase lag than in a higher inclination system. So we update this model by considering actual angle from observers azimuth angle and orbital inclination angle inside. We're able to reproduce the inclination and the energy dependence correlation. As you can see in the right panel, I show the simulated light curve from different radiums of jet, and the vertical line show the central maximum phase from the different energy of the light curve. So it gives you uneven angle phase lag difference between different energies. So it can well play. So and this update model can naturally explain the relation between the phase lag and the energy and the inclination angle. The next work will be the kilohertz field studies in SCORE-F1. So one of the most important discovery by Rose XT is the discovery of the kilohertz fields that opened a new window for the time analysis. So however, for the Rose XT, because of the limitation on the signal noise in the high energy band, so they can only analyze kilohertz fields in the energy band below 20 keV. More precisely, it will be between 9 to 13 keV. So by using the high energy data, especially above 20 keV, we're able to give an upper detection limit on these kilohertz fields, lower kilohertz fields in 20 to 40 keV. So this is the first time we have ever observed these kilohertz fields up to about 40 keV. So what does it mean? The discovery of this upper limit energy of the kilohertz fields has challenges existing models, because previously the lower kilohertz fields was believed to originate from the boundary layer of this part from between the neutron star and this accretion disk. However, according to the IMS spectrum of this source, and also the energy relation with this an IMS spectrum, and our result shows that this the boundary layer emission cannot produce the photons higher than 10 keV. So what is the possible location and the region maximum of the kilohertz fields? So we build this model, and we propose that the kilohertz fields could be caused by the clumps inside the inner part of the transition layer. Transition layer. It behaves like a bulk condensations, and it rotates at the subcapillary frequencies, which give you the lower kilohertz fields that you observe in the neutron star. So that's the whole explanation. The next work will be the choose of the Q diagram. So for anybody who knows black holes will be familiar with this Q diagram, HID diagram, which was I was shown before in the previous slides. And nobody has quantitatively studied what is the causality, what parameters contribute to the Q diagram. So what parameters cause the shift of the Q, and even they have a different spectral timing purpose at the same luminosity. So this work provides a very unique insight into the study of the Q diagram. They extract light curve from a different energy band, even from UV optical data from Insight-HXMT and U-Volt. They extract the light curve from about dozens of the energy range, and compared to the shortest wavelength, which is HE 20 to 150 keV. So they calculate the cross correlated function about this in the time domain of all these light curves compared to the HXMT 20 to 100 keV, the first one. So you can see the time delay is about 0. And when the energy increases and the time delay changes, and when energy increases to about 1 to 10 keV, the delay increases to about 12 seconds, 8 to 12 seconds. However, when you compare to the Swift data, to the optical and UV data, and the time delay is nearly 0. It doesn't change. So the possible explanation for this could be when the accretion disk when the accretion move inwards to the when the accretion disk move inwards to the black hole, the emission from both the corona and accretion disk they changes and the modulates, and the time delay could be caused by this different part of the emission between the disk and the corona. So this hypothesis can be easily tested by these following two plots. The first one is the total flux, and as a function of the parallel flux divided by the total flux, the parallel flux ratio. When you plot it like this, it's kind of like a typical HID diagram. So it shows the Q diagram in this plot. And when you correct it for the time lag that was introduced by the different energy of the light curve, you will see that it's become the linear function.
5 minutes.
For the disk components, you can see here it's about this. It works the same. If you correct for the disk emission time lag, then it will be corrected to the linear function. Then you will realize the source of the Q diagram is the time lag that's introduced between the relation of the accretion disk and the corona. So the last one is the type B QPUs in the max AG6048. So able to observe the type B QPUs in the energy range 1 to 100 keV, and the MS of this QPUs is about 7 keV. It's about 10, and it's about constant above 10 above 7 keV. The most important, it can well explained by jet precision models we proposed but for the time lag, we observed below 3 keV. You can see this is a 10 over. So we studied the Fitzgerald spectrum, and we found that there's a time lag between the disk emission, disk flux, and the compensation flux about 10 milliseconds compared to the time lag we observed in the low energy range. So this could be called the different the jet illuminates the disk at the different angle. They have a different part of the flux illuminated. And then you can also see the modular data at the red point here. It can well explain the phase lag energy correlation we observed in this source. And the other one is the sudden appearance and disappearance of the type B QPUs. When you compare the spectrum, you will see the disk flux, both the disk flux and the power flux changes. Disk flux decreases, also the power flux decreases. And in the 3D move close to the ISCO. This can explained by the disappearance of the B QPUs can be explained by the accretion disk moved outwards and a distant incorrect magnetic lines, so that could be caused the disappearance of the QPUs. The last one will be the reverberation lag study in the max AG1535. So we observe the soft lags in a hard intermediate state as here. And when you fit these characteristic frequencies within the latitude prefetching models can be well explained by this model, as you can see the function here. And when you compare the spectrum of these observations, you will see this geometry fixed in the truncated in the disk iridium from decrease from high state to soft state. I will give a short summary here. Very far, the small scale jet precessions is a very promising model explaining the high energy timing properties of type B and type C QPOs. And the lower critical QPOs is could be caused by the clumps in the inner part of the transition layer, rotated subcarbon frequency. And HXMT have very great advantages in the broadband variability study. Thank you very much. Grazie mille.
Thank you for this nice talk on a mission that we don't hear too much about, unfortunately. I'm sure there are questions, although I didn't see anything in this Slack. People online, could you please raise your hands? Okay. Yes, and Greg was first. Online, hang on.
Thank you, your reporter is here.
No. First, Greg Sivakov. He was indeed first.
All right, so I just had a quick question regarding these the small scale jet precession model. Is there a specific reason why we're seeing this in Maxi J1820 as compared to other sources?
Oh, this model is not limited just to 80-20. It can explain the IMS correlations and the time-lapse correlations in most of the black hole transients. Even we applied it to the Maxi G1631 and also a Maxi G3048.
All right, thank you.
Okay, Yuri, please.
Thank you, Jörn. So I would like to ask the question about this QPO, low frequency QPO that you detected in Scorpion X1. Because already like 20 years ago, for example, Gilfanov and Revnivtsev studied the frequency resolved spectra of a number of neutron stars where they detected QPOs up to 20 keV with the Rossi X-ray timing explorer. And it was clearly the spectrum of these QPOs were consistent with being produced by the boundary layer. So it's the argument that this boundary layer cannot produce the QPO that you see in Scorpion X1 is somewhat unclear to me, because I mean there is no big difference whether we have QPOs at 20 keV or like 30 keV. Is the boundary layer has the almost like a black body spectrum with the temperature, color temperature about 3 keV, so it actually goes to 30 keV easily. There is a lot of photons there, at least in Scorpion X1 there are plenty of photons still at 30 keV. Thank you.
For this question is because when you look at the IMS spectrum, you will see that here's the simulated IMS energy spectrum with the from HXMT data. When the energy is above 30 or 20 keV, you will see the IMS actually increases. Even we haven't detected the signals above 30 keV. But according to the performance, according to the ability of this detector, actually there is likely to have a signal here because just this source we don't have enough photons for this. We did a series of simulation. It could be the IMS could be increases above 30 keV. So that's why we apply this.
Yeah, 30 keV is the cutoff of the black body. Of course, this tail varies a lot, so there you expect the RMS will increase to high energies. And so I would suggest that you just plot the Fourier frequency result spectra and see how it looks at kilohertz frequency. And so you will see what is the spectrum of this component.
Yeah, that is a very good suggestion, but the problem that is we do not have a lot of photons above 30 keV. So that is the problem. Thank you very much for the suggestion.
Let's thank the speaker again.
Thank you.